Hello and welcome. In this video, I'm going to go over our final lesson for this unit. That's collision theory and reaction mechanism. All right, so the idea behind this you have heard before in this unit and in others. Particles are always in motion, right? You learned that back in grade 9, maybe even grade 8. They're always in motion, and for a reaction to take place, two things have to happen. So those two things importantly are that they must have the correct amount of energy, right? Even in something that is highly reactive, often let's say you're gonna light a match, you need that initial spark, right? So a minimum energy is required for the reaction to take place. Also, reactants have to when about to react, they have to collide in a certain orientation. So let's talk about temperature now. So we know that being introduced to this unit a little while ago, um, that kinetic energy is essentially measured practically with the use of a thermometer. So by increasing temperature, you can increase kinetic energy. By decreasing temperature, reducing thermal energy, you reduce kinetic energy. And what that will mean for particles is that particles with a lower amount of kinetic energy will travel, right? They're always moving. And if we use these arrows as symbols of the magnitude of kinetic energy, we can see that they have lesser magnitude than this, or lesser kinetic energy than temperature 2 here. So we'll have particles moving around, bumping into each other, colliding, and they may or may not have enough energy to react. Now, if we increase temperature, now they are still moving around, but this time they're moving around faster and with more energy, and those collisions might be more effective in producing a reaction. Okay, really driving this point home then, once they have enough energy, they do need to react, and maybe this reaction symbol is kind of confusing here. So if these two reactants are going to have enough energy when they actually do then react, if they need to react and collide a certain way, let's say a collision in this direction doesn't work. Nope, that's not going to yield a reaction. Well, they're going to have to collide in a different orientation. So let's say they have to collide like like that. Just making this up here. But let's say that is the correct orientation for the reaction to take place, and that will, with enough activation energy, with enough kinetic energy, that will yield a reaction. Okay, this is just a little prelude here to what we're going to see next. Okay, now I'd like to refer sometimes to a something a bit similar as a lock and key model for in your biology classes, like an enzyme and substrate. What is necessary for reaction is, of course, that orientation. So think of it for your bio students. Think of this as something similar, where for an enzyme to work, its reactants have to enter the substrate, enter the enzyme, and perfectly align in a certain way for the reaction to take place. In the enzyme or the catalyst will facilitate that orientation. We'll talk more about catalysts in just a bit. Okay, now you've seen these energy level diagrams now for at least a couple of weeks. What I haven't mentioned until now is what is happening at the very top. So you know this. You know that in this exothermic reaction, right, CO and O2 as reactants, we get a certain amount of energy for your reactants and certain amounts for your products. In this type of graph, this is exothermic. We would have a thermal release of energy. So heat is being transferred, energy is being transferred as heat, and we get a negative 226 kilojoule difference in enthalpy, or change in enthalpy, right? Activation energy, you know that it's from here to here. And what exists at the top here is what's called an activated complex. This is the transition state. You can think of it as when substances are colliding in the correct orientation, they create this activation complex, which has a much higher or a higher activation energy than its original reactants. It's very short-lived. It's a transition state from your reactants to your products. Some bonds are seen to be formed or partially formed or destroyed. It's just a transition to get from one to the next. Right, so these transition states can exist. We'll talk about that in the form of a fully worked out reaction mechanism in an energy level diagram. But these are these partially formed, partially broken structures that exist from one phase to the next. Okay, so better example here, we see reactants. Now they're increasing in energy here. Then we have an activated complex with, if you see this dotted line here, a partially formed bond, very energetically unfavorable, but it's transitioning to our products here. Okay, now to finish off that discussion on kinetic energy, we're going to look at what are called Maxwell-Boltzmann distribution curves. And if I label it here, I do. Okay, so at a certain temperature, I'm going to skip over here. At a certain temperature, most particles are going to have a certain amount of kinetic energy, right? So the likelihood of particles having whatever this temperature or kinetic energy reading will be, so whatever that temperature is, the likelihood of most particles being here is pretty high. But, so let's say this temperature is at, let's say, 10 degrees Celsius. That means that you will also have particles that are less than 10 degrees Celsius, and you'll have particles that are greater than 10 degrees Celsius. Now, usually when I'm in class teaching this, I may have a steamy cup of coffee in front of me or my thermos, and I probably made it an hour ago, and if my thermos is any good, it should still be nice and steamy. It's certainly not at 100 degrees Celsius at the point where water evaporates, and yet you would see from my cup, you would see steam coming out of it. Right? It's not at 100 degrees Celsius, right? You put a thermometer in there, it certainly would not read 100 degrees Celsius, and yet you see steam being released from the cup. That's because of these particles here that might be over 100 degrees Celsius. But my temperature would read, if I put a thermometer into it, would read below that. So same here, if your average kinetic energy temperature reading is 10 degrees, you would have some particles that are above and some that are below. Right, increasing these temperatures by 10 degrees generally will double a reaction rate. Right, because as you can see here, here is our activation energy required for reaction to take place. If you increase temperature, say from T1 to T2, the area under this graph here representing the number of particles at that energy is much greater in the red temperature 2 than in the blue temperature 1. Okay, with a little bit of calculus in the near future, you'll be able to, and of course a function for these curves, you'll be able to determine what the area under that curve is, and then math and chemistry gets a lot more fun after that. Okay, so that's Maxwell-Boltzmann. Right. Okay, now let's look at a reaction like this. Consider the reactants. You have 4 hydrogen bromides, or hydrogen bromine, it is a gas, and you have 1 oxygen. All 4 would have to collide with one of the oxygens in 2 ways. They have to collide with the correct amount of energy and the correct orientation. Now that's in 3D space, randomly hitting each other at the exact orientation with the correct amount of activation energy, minimum activation energy. That's highly unlikely for that to all happen in one step. So as we've talked about in previous units, this has to happen in different steps. So what happens in these steps? First, we get HBr with oxygen at a certain activation energy, and that produces a reaction intermediate or transitionary substance here. And that will react then with HBr and produce another transition state that will react with itself and finally produce products. Using Hess's law, we can begin to cancel things out and we get our overall reaction right here. Okay, now I can get rid of this because what I've done here, just delete that. Okay, I've assigned arbitrary numbers. Now these definitely are not the enthalpies of these reactions. If you look this up and you say, what's wrong? This is definitely not it. It definitely is not it. I just wrote these in about a minute ago. Well, maybe a bit more than that, but not too long ago. It's just to help us draw a graph, which I have already drawn here for you, but I'm not going to refer to that right away. I'm going to make a new graph because although I can just show you, yeah, here's the answer, I go over it, I think it helps if I draw it for you. Okay, I want to draw a straight line. so let's start. Okay, here's a straight line. Perfect. Okay, now our first reaction, HBr and O2. All right, we're going to say this represents kinetic energy, and this represents progress of the reaction. So we can say time, but I'm just going to say progress of reaction. All right, let's say it starts about here. Notice there's no exact scale here. It's just to show you. Okay, so it starts off at approximately there. And our reactants are HBr and O2. Okay, now they're going to react, but like anything else, they need an activation energy. Now, they're going to react in an endothermic way. So the product HOOBr is going to have more energy than the reactants. Okay, so that means activation energy and here. Okay, so the product was HOOBr. What we see here is our activated complex right here. What we also see is what you've seen in the past, our activation energy represented in green right here. This is our first step of this reaction mechanism, but we have to continue. Next reaction. Okay, now this is going to be exothermic. So HOBr is going to react with HBr. Okay, that does need some activation energy, but it's an exothermic reaction. So our products in this case are going to be lower than our reactants. So it's still going to need a certain amount of activation energy, but now we've lost, right? We've lost some energy, and we get, oh, I should write HBr reacts here, right? HBr with HOOBr, we get HOBr. Okay, before I continue, want to make sure to not forget to include something. This difference in our first reaction from here to here, this is our first enthalpy. Difference in enthalpy, enthalpy 1. And in our case, I believe that is 10, that made up number there, 10. Okay, and now from here to here, let's just try to keep this as neat as I can. Our second enthalpy is going to be -5 kilojoules. Okay, and for a exothermic reaction. I know not to scale, it's really bad, but just bear with me. Okay, continuing. Next reaction is also exothermic. It's going to decrease in energy. Okay, we do need an activation energy. So up here, and then it dips quite a bit, and we're done there. Okay, so let's start labeling before I continue to forget. All right, so here was another activation energy. Here is another activated complex right here at the very top. Here is another activated complex right here at the very top. And green for activation energy. So here was my activation energy. And this will be from here to the products. This will be enthalpy. Call that delta H3, which I believe was -25 kilojoules. Sorry, 20 kilojoules. Okay. So HOBr reacted with itself and it produced, oops, wrong direction, water and Br2 as our products. Okay, this is now an energy level diagram that represents a three-step reaction mechanism for an overall reaction that is in this. This is our target equation if you want to use the same language as we did with Hess's law, right? Let's see if I missed anything here, right? Our activated complexes are there, our intermediates. I should highlight these. Our intermediates are here, right? And here, those are our intermediates. our enthalpies, right? One thing I noticed, talking about kinetic energy and temperature, wrong. It should be potential, always potential, potential energy. Here we're talking about the substances themselves, not a measure of the thermal energy. So that's, I'm glad I found that, and we can make that correction here. Okay, good. So HOOBr and HOBr, these are our reaction intermediates that we mentioned. Along every step, we have activated complexes. Our rate determining step, which can definitely get more involved than this simplest definition here. What I didn't point out is that we can have this qualitatively labeled as slow, fast, slow, as I have here. Now, here we can't determine exactly which one is our rate determining step. All we can say is that 1 or 3 are our rate determining steps. If they are slow, or if one is slowest, let's say if one is slowest, then 1 would be our rate determining step, our first step here, because it is the slowest, right? So we can determine our rate determining step by looking at the overall reaction mechanism. Now, admittedly, there's another way of doing this, looking at the overall rate law, but we're not doing that right now. Okay, we talked about our transition states, talked about our activated complexes. It's for later, and that's it. Here's your home fun. Post any questions. I hope this helps.